Okay, good afternoon, everyone, and welcome to the last session of our 2023 ASA SLDS webinar series. It's been great to learn a lot of stuff with you guys during the year. So if you have any suggestions, questions, comments, feel free to let us know. Either you can send me an email or you can comment in like our YouTube page, or if you have any suggestions for our 2024 session, you can comment or send me emails. Okay, so today we are pleased to have Dr. Weijie Su from UPenn. Weijie is an associate professor in the Wharton Statistics and Data Science Department. He's also a co-director of the Penn Research in Machine Learning Center. Weijie got his Ph.D. in 2016 from Stanford. He's a student of Candes. Weijie's research interests include privacy-preserving data analysis, deep learning theory, statistical aspects of large language models, and high-dimensional statistics. Despite his young age, Weijie is a widely recognized expert who has won many awards. He's a recipient of NSF CAREER Award, Sloan Research Fellowship, the IMS Peter Hall Prize, the SIAM Early Career Prize in Data Science, and the ASA Gottfried Noether Early Career Award. He also serves as associate editor of JASA, and today he's going to talk about a regression approach to peer review in NeurIPS and ICML. Let's welcome Weijie.
Okay, thanks, Zhihua, for the invitation. It's my great pleasure to give a talk at ASA LDS webinar. So I'm going to talk about my research to improve peer review in machine learning. So this is a number of submissions to NeurIPS, and so this was a little bit outdated. So this year, the number of submissions I remember was 13,000. I was just back from New Orleans attending NeurIPS this year, and this is typically what I see, and it's really full of people. And this year, the number of people attending NeurIPS was, if I remember, like 15,000. Crazy. But this really creates a huge burden to peer review in machine learning, and to handle 13,000 papers within like 1 month, and it really requires tons of a very large number of reviewers to do the job, and which is difficult because simply there's no such many experts in the field to handle this amount of review. And so there's already lots of complaint about peer review, the decline of peer review quality. So back 2014, and there was an experiment at NeurIPS. Some papers were randomly assigned to two different sets of reviews, they were not known to each other. And so this shows that for majority of the time, the two sets of reviewers actually wouldn't disagree with each other. So this means that in this part, one set of reviewers said, yes, accept this paper. And the other reviewers say, no, let's reject this paper. So whether this paper would be accepted or rejected really depends on which side of the reviewer it was handling the paper. And so it's really, people need to be very lucky in order to be successful in machine learning. And a lot of prominent people in machine learning had complained on Twitter about the quality of peer review. And last year, there was even a little bit controversial about the outstanding papers at ICML. And so this peer review in machine learning is slightly different than peer review in statistics, which is the primary venue is a journal. In machine learning, the primary venue is conferences such as NeurIPS, ICML, and ICLR. And so the most important factor to reject or accept the paper is the review ratings. Okay, review ratings. So typically a paper will be reviewed by 3 or 4 reviewers. Each one will rate the paper from the scale 1 to 10 or 1 to 8. And you see, if the average rating is high enough, and the paper is most likely to be accepted, and otherwise it will be mostly likely rejected. But however, this is not a single threshold. If the rating is high enough, it's likely to have a oral presentation. Even high, it will perhaps get a best paper award. So yesterday I was attending NeurIPS, and it's crazy. So even for a normal session where a paper, an oral presentation would be accepted, and I saw that there was about 1,000 people attending the work, attending a oral presentation. And so the influence is huge, meaning that if a paper is presented at NeurIPS as an oral paper or best paper, and soon the paper will accumulate several hundred or even thousand citations very soon. And so there's a subfield in machine learning and to improve peer review. And but most of the effort was trying to recruit more reviewers and encourage the reviewers to spend more time on reviewing the paper. From my side, it's this is perhaps a little bit if too much, because the supply of good reviewers is basically limited. So this is a very scarce resource. And it's hard to expect that the reviewers could spend more of their time. So instead, is it possible to look at from a different angle, to look at, is there any other resources to improve peer review? So this is actually the authors. Presumably, the authors know the papers the best, because it is the authors who write their papers. And this is my own experience. And I typically submit several 2 or 3 papers to NeurIPS ICML. And it's often the case that my good papers get rejected and my bad papers got accepted. It's very random. And I also had a poll on Twitter, so asking whether they feel peer reviews in machine learning helpful. Most will say yes, helpful. But when I ask a different question, have you ever seen any reviewer seems to know more about your papers than you do? Most people say rarely or even never. So machine learning is slightly different than statistics, where in machine learning, most reviewers actually are PhD students. So certainly we cannot expect them to provide very helpful comments to improve our papers. The reality is that they typically know much less about our papers than we do. So, but however, if we directly ask comments, opinions from the authors, it's a little bit difficult to make sure that the authors will be truthful, will be honest, right? Because we all have the tendency, we all have the interest to say good things about ourselves, right? So this is unfortunately the story behind the Boeing 7, the Boeing Max crashed 2 times 5 years ago. And the latest investigation showed that actually FAA designated Boeing to self-evaluate their own product. So in this manner, Boeing was not fully honest. So seems this is a game. On the one hand side, the authors knows much about their products, their papers. But on the other hand side, they are less likely to be truthful, to be honest. How can we make it truthful? So this is going to be a game. So in this game, Alice is our author. She writes many papers to a single conference each year. And Bob is the conference organizers, and he wants to estimate the true quality of Alice's papers. Suppose that this is our main hypothesis. We assume that Alice knows about the true quality of her papers. Okay, the true quality of her papers. The true quality of her papers are given by R1 to Rn. Suppose she has N papers. And but Bob only observed some noisy review ratings. Okay, Yi is the noisy review rating, which is Ri, the true quality, plus Zi. Okay, and they want to then noisy variables. Okay, and Alice does not observe the review ratings until she makes some decision. Okay, ultimately she will observe the review ratings, but she will observe later. But for Bob doesn't know the true ground truths R, doesn't know the ground truths R. R here is a vector of R1 to N. He only observes the rating, the noisy ratings. So this is our problem statement. Can Bob estimate the ground truth R1 to Rn by asking some questions from Alice? Okay. So at least this should be at least be better than the original raw estimate. Why? Because Y is just the original rating, right? Original rating. So there's nothing to, it's already available. So we should at least outperform Y. So essentially we want to improve MLE. So the first question that how can Bob formulate this question, right? And what kind of question can Bob ask? And next, when Bob received answers to Alice, how can Bob incorporate this information into the estimation? And last, what does Alice want, right? In this manner, certainly Alice doesn't want estimation. Okay, Alice wants to make her papers all accepted. Okay, so this is a problem statement, and Yi is the true quality, Zi plus Zi. So here, if some people don't feel comfortable to have a numerical rating to represent the quality, we can think that Ri is the, for example, true rating. Suppose one paper is reviewed by, a paper is reviewed by 1 million reviewers, 1 million. And then Ri is the average of these 1 million review scores. So this is a kind of the population average of the review rating. Okay, so here this is the address for the first question, and so we partition the whole space Rn into several different disjoint sets. Okay, so essentially the question is about where the vector R1 to Rn is, right? So we can partition the whole space into several different sets. So as long as we tell that one Si contains the ground truth R, so this is a question. So suppose Alice's answer is S. Suppose S is an element from S1 to Sn. Okay. So then Bob has to trust Alice. So what the Bob does in estimation is to solve this statistical problem. So in this problem, it's basically Bob wants to find R, a vector such that it is very close to the observation Y in L2 norm. But meanwhile, it should also force on the set S, because Alice tells Bob that, okay, the ground truth is in S. Okay, so this is basically shape restrict estimation in statistics. Essentially, it's to project Y onto the set S. Okay, and the third, what does Alice want? So here we assume that Alice wants to maximize her utility. So the utility is additive across all her papers. She has N papers, right? And so each utility is a function of the final review rating, Ri hat. Okay, R hat is a solution to this statistical problem. It's to this shape restrict estimation. And U should be, of course, be an increasing function. The higher, the better. But it's random, right? Because there's some randomness from the review ratings. So that's why we take expectation. So this is her utility. So Alice wants to maximize her utility by reporting some S. She might lie. She may not be truthful. Okay, she just want to maximize this utility for any S in this set. Okay, so there are several examples. And for example, if the partition is a singleton, so every set contains a single point. So essentially, we are asking what's the exact value of R. And we can also be a little bit coarse. So this is the first option. This is remaining. So in this question, we are asking whether all the entries of R is non-negative or above some threshold, okay? Because we can replace by 0 by 5, for example. And here, we partition the whole space into n different sets. And each I, xi, the ith paper is the best paper. Okay? So this is essentially to ask Alice, which is your best paper? Which is your best paper? Okay, so we can ask, for example, whether you are in the United States. So this is a very general question. We can also ask which town are you from? So this is a very fine grained. And in the middle, we can ask which state are you from? So this is neither too coarse, neither too fine grained, something between. Okay, so why do we want this information from Alice? So the answer is that message is that if Alice is truthful and the S is convex and really contains ground truth R, Okay, if Alice is truthful, then S must contain ground truth R, and then Bob will always improve estimation. Okay, so the MSE using the estimate from Bob will be better than using the original estimate Y. Okay, and but moreover, we also want to ensure that R set is as small as possible. Okay, the smaller the better. Okay, if someone tells me that you are in Pennsylvania, okay, and the search space is large. If somebody tells me that you are in Philadelphia, then the search space is much smaller. So the estimation will be much accurate. So this is confirmed by this simple query. So in this query says that if there are two cones, and the one cone is smaller than the other, S1 is smaller, S2 is smaller. So in this case, the estimation MSE of S2 will be smaller than the MSE of S1. Okay, and so we have, so this is what we want to. We want to ensure that Alice is truthful, okay, so that the ground truth is really in S. And meanwhile, we hope that all the elements S should be as small as possible. Okay, we hope that this partition, knowledge partition, is fine-grained. Okay, and but now how can we make sure that Alice is can be truthful and also have this fine-grained partition? So this is not easy, right? So we need assumptions. Our first assumption that Alice knows the ground truth. Okay. And Alice knows sufficient knowledge to determine which knowledge element S contains the ground truth. In this case, she does not need to know the whole vector. Okay? She only knows as long as she can determine which S contains R, that's sufficient. And second, we assume that noise term they want to then ID draws from some probability distribution. This ID can be slightly relaxed to exchangeability. Okay, and the noise can have mean non-zero. Okay, it's not necessary to be unbiased. And later we can also show that as long as they want to then follow some exponential distribution, it's also fine. And the last is the most crucial. We assume that the utility function is increasing, but it's also a convex function. Okay, and this convex assumption, let's elaborate on this convexity assumption. So this convexity assumption basically said that Alice prefers to have a very bad paper and a super good paper as opposed to two mediocre good papers. Okay, and so this is perhaps is really the case in big conference such as NeurIPS. Now this year NeurIPS had maybe 3,000 or 4,000 papers accepted. Having a paper accepted really means little, doesn't mean too much. Okay? Because for a poster, very few people will pay attention to. But if this is a spotlight, maybe several hundred people will pay attention. With the oral presentation, maybe several thousand. If a best paper, maybe the whole machine learning community with several hundred thousand people will pay attention. And so the attention is increasing exponentially if we have a higher category of acceptance. And this is perhaps also the case for very valuable things like diamonds. And if the grade is higher, and the price will increase dramatically. So now let's present our first theorem. Our first theorem is saying that under the three assumptions, in order to, if Alice is always truthful, then the knowledge partition, the questions we ask Alice, must satisfy the following assumption. The question must be pairwise comparisons. Okay, that's it. Must be pairwise comparisons. The knowledge partition must be cut by pairwise comparison hyperplanes, such as xi is equal to xj for some I and j. So this means that for Bob, the only valid question we can ask Alice is to pairwise compare her papers, such as, okay, you have submit 10 papers, fine. Whether your third paper is better than your fifth paper, just tell me which is better. Okay, and you cannot tell me that both of your papers are great. It's not accepted. You can only tell that which one is better than the other. Okay, so you cannot have your cake and eat it too. Only comparison. Okay, only comparison. And so this is the comparison actually has one more advantage than absolute valuation, because comparison is basically free of calibration. Because here we only needed to know a monotone transformation of Ri, okay? And so this is sufficient for us to say which paper is better than the other. Okay, so now let's go back. So if we ask what's the exact value of your credentials, of your paper's quality, okay, she will lie. She will say all her papers are the best. And all the entries are non-active, all your papers, for example, has quality high rating, true rating higher than 5. People will say yes, right? So it's not going to be truthful. And what's norm of R? Yeah, it's not truthful. Is this like such inequality? It's not truthful. Yeah, this is not truthful, although it's a comparison, but there's an intercept 10, so it's not truthful. So which entry of R is the largest? So essentially, which is your best paper? In this case, it satisfies the necessary condition, but still not sufficient, right? We don't have the sufficient condition, but later we will prove that this is sufficient. Yes, this is true. Alice will be truthful in this case. Okay, so there are some intuition. The intuition when we have two papers, okay, and so if we ask Alice, instead of asking Alice to compare which is better, for example, if we ask Alice the value of R1 minus R2, okay, how much better is your first paper than your second paper? Okay, tell me the difference. Okay, in this case, the partition is just all the lines with 45-degree line. 45 degree. So in this case, Alice will say infinity. Okay, infinity. And so this is because look at this simple statistical problem, shape residual estimation. The solution will be like as follows. Her relatively better paper will have rating high enough, and her relatively worse paper will be very worse enough, minus infinity. Why? This is because in this solution, in this convex utility, we would prefer to have maximize the overall sum, right? Overall sum. So for convex utility, and the utility will be higher if the two numbers are far apart when their mean is fixed. Okay? So in this case, Alice will not be truthful. Okay. So now we get a necessary condition, but now let's try to get sufficient condition. Okay, sufficient condition means that let's prove that in certain cases, Alice will be truthful. Okay, but before proving this, let's first ask this question: which is the most fine-grained possible truthful knowledge partition? So this is going to be all the rankings, right? All the rankings. Why? Because if we do all the pairwise comparisons, and this will give the most fine-grained partition. And if we do all the pairwise comparisons, essentially we know which paper is the best, which paper is the second best, which paper is the worst. So we know a ranking of all her papers. Okay. So when we know all the rankings, and then it's possible to like build up all the other truthful knowledge partitions. Okay, because of the previous necessary condition. Okay. So that's why all the rankings are basically the basic units. Okay, and let's start. So now let's create isotonic mechanism. So this is essentially to ask Alice to provide a ranking of all her papers from the best to the worst. So this is the mechanism. Y is the original rating. Okay, this is L2 norm, and the pi 1 to pi n, it's the coordinate index of her papers, such that Alice believes that the quality of her papers in descending order. Okay, descending order follow these indices. So this is the best paper. This is the worst paper. And we call it isotonic mechanism because this is just isotonic regression. Okay, this is isotonic regression. So I have a friend who submits 6 papers to NeurIPS. Okay, and I asked my friend to rank his papers from best to the worst, and this is original ratings, scores he received, and this is decision. Okay? Decision whether reject or accept. After applying the isotonic mechanism, and the ratings look like as follows. Okay, so my friend told me that he would prefer to have these 3 papers accepted instead of these 3. Okay, so now we have this theorem to ensure that the isotonic mechanism is really truthful. Okay, so the statement is very simple. If we on the 3 assumptions for Alice, in order to maximize her utility, she must tell the true ranking, high star, which really sorts her papers in descending order of quality. Okay, so this is so again, to provide a ranking, it's sufficient to know a kind of monotone transformation of R anyhow. So it's free of calibration. There's no calibration issue. Okay, here utility is a convex utility is necessary. Without convex utility, this theorem won't hold. And together with the previous necessary condition, and we have this theorem. So this theorem says that the best truthful question we can ask Alice is just to ask her to provide a ranking. Okay, so n factorial such isotonic cones form the optimal truthful knowledge partition for us. Okay, okay, so this is perhaps the main message of the talk now, and maybe I can stop a bit for any questions.
Okay, feel free to type any questions in the Q&A session, or if you want to talk directly to Weijie, just raise your hand.
Yeah, if you have any question, and also you can save question for the end of my talk. Okay. Maybe I can move on. Okay, so this is some proof idea. Maybe I can skip the proof idea because okay, I've got a question. I was anticipating a practical application of your proposed. Yes. So I will show that there's some application. Yes. Okay, so here intuition that so why Alice should provide a true ranking? Alice should provide true ranking. So this is really can be seen from the power algorithm for isotonic regression. So isotonic regression has this very nice algorithm, which I enjoy very much when I learned it. So first we sort the observation according to the ranking. Okay? If this is already in descending order, then we are done. Okay, but unfortunately, in general, it's not the case, right? So there are some subsequences which are still increasing. So what we do is to replace the average subsequence by their average. And but if this is not is this in descending order? Not yet. So there's still a increasing subsequence. So let's average again, and finally let's average again. So now it's the solution. So now it's in descending order. Okay. So in this business, you see that if Alice tells the true ranking, so there will be less number of steps to average, right? If she tells me the opposite ranking, and then after averaging, so everything will be flattened out. Okay. Any question? I have a question. What if most people submit only a single paper and only a small number of submit? Yeah. So at ICML, half of the author, basically nearly half of the authors will have at least 2 papers. And more interesting is that for most of the papers, at least one author will have more than 1 paper. I have one more question. Okay, so this shows that if Alice doesn't tell the true ranking, so then it's more likely to average everything out. By averaging more, then she will have the utility will be lower. So for example, if Alice has 2 papers, one is much better than the other. If Alice is honest, then so she good paper will be accepted with perhaps an oral presentation with 1,000 attendees, and R2 and the second paper will be rejection. But if Alice lies and then will average out R1 and R2, she perhaps will only get 2 posters accepted, with only maybe a couple of people watching stop by her posters. So this is our estimation. So this has a little bit statistics and a result due to Professor Chunghui Zhang and about isotonic regression. So roughly speaking, for isotonic regression, the performance will be very good if n, the number of paper is large, and meanwhile, sigma is also large. Sigma large, being large means that the review rating are very noisy. And the n means that a paper also is very productive. And now let's take a look at how n could be look like for in peer review in machine learning. Okay? So this is the number of most productive authors in machine learning. So they are all very famous, well-known researchers in machine learning. And so this is the case for ICLR 2020. By the way, ICLR 2020 is the smallest, is the third largest conference, and after NeurIPS and ICML. Even for the third largest conference, and the most productive author, Sergey Levin from Berkeley, had 32 papers accepted in one shot to a single conference in 1 year. And so last year, Dan Roy, my friend from University of Toronto, he tweeted that he had 132 papers accepted to NeurIPS at one shot. So I followed him, we followed each other. I asked Dan, is this a joke? Are you really submitting 135 papers? If so, can you rank your 100 papers? And he said, this is not a joke. He was very serious. He really did submit 135 papers in a single conference. And this is because he was running a big machine learning conference with more than 100 undergraduate students. Every student wrote a paper with him and submitted to NeurIPS in 2022. Okay, and he said they are all ranked #1. They are all the best papers in the world. Oh, I have one more question. Yeah, does the true ratings needs to be on the ordinal scale with distinct unity? It needs to be continuous. Oh, thanks for question. And the true ratings, original rating, a single rating is an integer value, ranging from 1 to 8 or 1 to 10. For NeurIPS and ICML, it's from 1 to 10. For ICLR, if I remember, it's from 1 to 8. Yeah, you're right. It's a approximation, right? Because here we assume that the noise follows some distribution. Of course, this is some approximation we use in our assumptions. And second, can I assign equal ratings, or it needs to be increasing or decreasing? Is there a limit to n? And no, n can be as large as possible. Second question is a regular question. Yes, Alice can say Alice can only provide a partial ranking. Okay, partial rank is not necessary to rank all her papers. Okay, anyhow, it's a joke. And a joke. Okay, so last year the most productive paper also finally came out, and Dan Roy was not on top. Okay, I look at the accepted papers. Dan only had 2 papers accepted, only 2. So which is a small number compared to these very productive authors in machine learning. So we have some extensions addressing some of the questions raised by the audience. And will be Alice, if Alice doesn't know the true ranking, the whole complete ranking, she still can do it. She can provide a partial ranking. And what if ratings are generated from other models, not, for example, not from a continuous model, from a discrete, for example, exponential family model, for example, is it possible? Yes. And what if Bob doesn't know which nudge partition to use? If he has multiple, yes, we can still do it. What if Alice utility is not additive? In some cases, we can still do it. And what if utility does depend on the ground truth? Okay, so far utility is a single function of R hat, and we can also do this in this case. Okay? And suppose what if the papers are owned by multiple owners, right? Because a paper typically is authored by more than 5 papers typically in NeurIPS. And in this case, we can still do it. And no one knows the true ranking. And in this case, you can still do it. Okay, so there are several examples. So this example shows that in this case, Alice will not be truthful, although this is still partition. Okay, this is a single isotonic cone. This is the rest. In this case, Alice will not be truthful. So this means that we should be very careful when we want to form truthful knowledge partitions. But there's some example. Here, the example is that she can partition the papers into different categories. And she can say that this category of papers are better than this category of papers. But she doesn't need to compare papers within each category. She doesn't need to do it. Okay. So essentially, we can see that any element in this subvector is larger than any element in this subvector. She doesn't need to compare elements within this this group. Okay. And for example, in this case, Alice can just tell me, okay, what are the top 10% papers and what's the next top 10% papers. She doesn't need to know, doesn't need to tell me all the complete ranking. Okay. She can also tell me which half of the papers are better than the other half, okay, for example. So in this case, Alice will still be truthful. Okay. So this is our theorem. The theorem says that in this case, Alice will still be truthful if we ask her to provide a partial ranking. Okay. So this is joint work with Professor Jianqing Fan and his student Yulin Yan. So roughly speaking, because we don't have too much time, I will be short about the extensions. So roughly speaking, we can still extend the isotonic mechanism to exponential family distributions. The isotonic mechanism will still be truthful, okay? And moreover, so it will still be basically, in some sense, ranking will still be the optimal question we can ask. Okay, but a good point about this mechanism is that the mechanism still takes the original form of the isotonic mechanism. So Bob doesn't need to know the exact probability distribution of the exponential family distribution. He does not need to know the distribution. And the mechanism is free of the specific form of the distribution. So this is so if somebody tells me that someone will get a best paper award, and usually many people, as far as I learned, many people will be worried, because nowadays it's often the case that some paper gets best paper award, and later people will read this paper very carefully and find some mistakes. And this is has been increasingly the case. So last year there were two papers, 10 papers got best paper awards at ICML, and later 2 of the papers were found to contain some issues. Okay, and people discussed a lot on Twitter, and which was a little bit sad for the community. And this year, ICML had one best paper award, which were later found to repeat something people already discovered 10 years ago. So in this case, we have to assume that the utility depends on the true quality. Okay, if the true quality is high, the utility will be higher. So in this case, Alice will still be truthful. Okay, so all our story means that in any cases, Alice should be truthful when she is asked to rank all her papers. Okay, so although in some cases we have to admit that the utility will not be convex. Okay, because this is, for example, the case many my junior colleagues will tell me that, and junior students told me that they only care about the number of accepted papers. When the ratings is high enough, and when the paper will definitely be accepted, there's no much motivation for them to further polish the paper, to further improve the paper. Okay, so this is the current situation in machine learning. And however, perhaps the machine learning community should do something to improve, enhance their community. For example, and should make it clear that now having a paper accepted at NeurIPS doesn't mean too much. Okay, so this year there were more than 3,000 papers accepted. Meanwhile, there should be some channel to highlight some good papers from these too many papers. Okay, so in a way to encourage people to further increase the quality of their papers. And also, maybe it's a good idea to use open review for all machine learning peer review, and make it public, make the review outcome, also make the review comments public to anybody. And so in this way, people will have impression about good papers. If the good papers get good review ratings, and the impression will be positive for a long time. And for a joke, maybe we can also ask Elon Musk for help. If he can offer this amount of money to everybody with this rating, so this is a very convex function. And in this case, everybody will be sufficiently motivated to provide the true ranking. Okay, there are many other reasons to use this mechanism. For example, and people will, when I give this talk, I often receive this following comment. People say papers cannot be compared. Okay, yes, it's true, but look, NeurIPS ICML just accept 20% of the papers. So essentially, it's to compare papers with others, right? So we are comparing whether the paper is above the 20% portion. Okay? So nevertheless, we still need to compare. Okay, and the good thing about conference papers is that conference papers are easier to compare than journal papers. If the utility is not convex, in principle, there's a room for author to gain, but maybe for most authors, they will still be truthful. They will still be honest. Okay? And meanwhile, the ratings can only be known to senior area chairs instead of the area chair. And this might discourage guest authorship, because if somebody knows nothing about their papers were invited to as an author to the paper, and the ranking given by this author might not reflect the true quality of this paper. So other authors might be afraid of inviting additional authors. And most importantly, it's because the current system is really failing. Okay, so at NeurIPS, nobody. I just was back from NeurIPS. Many people complain about the review quality. Okay, so there's a strong consensus that the current review system is not working at all for handling this amount of papers. Okay, so we have experiments, and we have written the report, and the report is pending the program chair's approval. When we get approval from the program chairs, we will upload our paper to ICAP. But meanwhile, I can show just some basic information from our report from ICML 2023. Okay, so we are very lucky to get approval from the program chairs of ICML this year, so that who allow us to do our experiments. So this year, ICML received 6,500 papers, which is the second largest conference in machine learning. So we developed a website, OpenRank, for doing these experiments, which is a collaboration of the Open Review website, which hosts the peer review of ICML. So this is our website, and this collaboration effort with my student, Jaya, and a Penn student, CS background student, Natalie, and my CS colleague, Aaron, and Xiao Liman from Harvard, and this is me. Okay, so we send an email to every author of ICML, just passing the deadline. So, and when we click this link, and this will give you this page. Okay, so this year I submit 2 papers to ICML, and you can, on this webpage, you can drag down or up to rank your papers from best to the worst. Additionally, we also have some additional questions for every author. Okay. And so about half of the authors attempted to do experiments, and some made it successful, some didn't. Okay, and we didn't analyze the data until April 22 because we don't want to interfere the decision making. This is a date where the announcement, the paper rejected and the accepted decisions were made. Okay, so these are some basic summary statistics from our study. Okay, this is total number of submissions, and the total number of authors is 18,000. And the number of authors, so this is the number of authors, yeah. And this is the number of submissions with at least one author having more than one submission, okay? And this is a little bit low, but this is very high. This means that for most papers, at least one author will have more than one submission. And this is the decision outcome, okay? And about this amount of papers were rejected immediately. And this was rejected later, and this was amount of papers accepted. Among these accepted papers, and this was a fraction of papers accepted as oral presentation, and this was paper accepted as a best paper. Now look at our response rate. So our response rate was basically 30%, okay, 30%. And 5,632 authors responded to our survey experiment, okay? Among these, 1,342 papers for authors had at least one paper, more than one papers submitted to NeurIPS, to ICML. So that's why, which allows them to rank their papers. Okay. And in total, our experiment involves 2,592 submissions. Okay. And so the number of reviews on average, every paper receives 3.08 reviewers. Okay. So the longest ranking we received from our experiment is 13. Excuse me, this is 17. So this is our preliminary results. Okay, and here this shows the MSE, mean square error, and the mean absolute error. So this is mean square error, L2 norm. So this is the mean absolute error, L1 norm. Okay, and so here this is to show the error using the original rating and the isotonic rating. But of course, anybody will be wondering, there's no ground truth, right? Yes, this is the case. So what we do is to compute a proxy error. So the proxy error is basically to estimate one error and divide minus the other error. So a paper typically receives 3 review ratings, okay? And so, for example, we partition the review ratings into 2 groups, one rating and another 2 ratings. So we basically apply the isotonic mechanism to the 2 ratings, the average of the 2 ratings. And now we want to predict the remaining, the holdout rating. Okay. So the idea is that although the ratings are very noisy, but they are still unbiased. Okay, so their mean is still the same in a overall sense, in a marginal sense. So which allows us to measure the performance of the method by looking at the difference of the isotonic review rating and the holdout review rating. Okay, we see that basically our isotonic review score will have a smaller error for any number of submissions group. Okay. So this is to partition the authors into depending on how many papers they have. Okay, whether they have 2 papers, whether they have 13 papers. Okay, no matter how many papers each author have, on average, we will improve the error. Okay, so the improvement will be more significant if we are using L2 norm instead than L1 norm. Okay, so this is the response rate depending on the number of submissions. So roughly speaking, if for more productive authors, they are less likely to submit our experiment. So this is expected. This is what we expect, because for more productive authors, they are very busy and they usually don't respond to any such experiment. Okay? Because we cannot require them to, we cannot force them to provide a ranking. Okay, and so we will do this experiment 2024 because the program chairs of ICML 2024 see some positive results from our analysis. So they allow us to do it again next year. And the next year, we will try to do perhaps more refined analysis from the experiment. And hopefully we can get more positive information to support our mechanism. So the ultimate goal of our team is to make it real in practice. We hope that in the next few years, our mechanism, the ranking mechanism, will really be used in practice for machine learning conferences such as ICML and the NeurIPS. Okay, so it's a joke, and so at the beginning, so the program chairs this year allowed us to use our ranking for decision making in some case. But later, and there's lots of discussion on Twitter about our method. Many people were not happy about our idea. And really, it's really because they only look at the first few lines of our experiments. They thought that it will be the author to review their own papers. Okay, they will think that the author will decide whether to reject or accept their papers, which will, of course, will be funny. Really, it's our papers are not let author to review their papers. It's only to ask author to provide a ranking to facilitate peer review. And so even some Chinese social media were discussing our methods. Okay, and so because of this pushback, and finally the program chair decided to do the rankings will not be used in decision making. Okay, so this tells me a lesson that we should be very careful doing such big experiments, because it will influence hundreds of thousands researchers in machine learning community, which is huge. And so we hope that we will do very careful next time, and gradually we will collect more positive experiments to convince people that this is a experiment worth using in practice. Okay, and our method can perhaps be extended to other settings where, for example, you know the best. Okay, so this is a soccer, and the program like manager, coach like Guardiola perhaps knows anybody else than his own players. Okay, he perhaps knows that some players should worth this amount of money instead of this amount of money. Okay, and this information will be very valuable for some companies to value each player. Okay, but of course, Guardiola perhaps won't tell the truth. Okay, and the idea is that how can we elicit useful information from people who know the best. Okay, so this is second-hand market. So second-hand market is also an example that the previous owner knows the quality the best. Okay, but how can we elicit this information truthfully? Is a question. Okay? So this actually offers a future framework for statistics. Okay, so Alice, for example, knows the true parameter and which generates the observation, and Bob wants to estimate from observation to estimate the true quality theta. And can Bob ask some questions about theta from Alice? Okay, so that's a question. In the future work, and we hope to extend this to multiple owner settings in a more realistic way, and hopefully to relax convex assumption. And instead of using for peer review only, we hope that this can be also used in other settings like recommender systems, where an influencer often submits multiple videos to YouTube or TikTok. Okay, and this is the references, and I think I'm done here, and thanks for your time.